What is a p-n junction? If a piece of intrinsic semiconductor is doped so that one part is n-type and the other part is p-type, then a p-n junction is formed at the boundary between the two regions. This p-n junction is a basic building block for many electronic devices. Now, look at this figure. This is the basic silicon structure at the instant of junction formation, showing the majority and minority carriers. This is N region, where the majority carriers are free electrons. This is P region, where the majority carriers are holes. And this is p-n junction, which is formed at the boundary between p and n regions. These free electrons in the n region near this p-n junction begin to diffuse across the junction and fall into the holes near the p-n junction in p region. Now we will understand what is the depletion region. When the p-n junction is formed, the n region loses free electrons as they diffuse across the junction. This creates a layer of positive charges, that is, pentavalent ions, near the junction. As the electrons move across the junction, the p region loses holes as the electrons and holes combine. This creates a layer of negative charges, that is, trivalent ions, near the junction. These two layers of positive and negative charges form the depletion region. Now, look at this figure. For every electron that diffuses across the junction and combines with a hole, a positive charge is created in the n region and a negative charge is created in the p region, as you can see here. As these free electrons continue to diffuse across the junction, more and more positive and negative charges are created near the p-n junction, forming the depletion region. These blue arrows between the positive and negative layers represent the electric field. As you can see, it is from N region to P region. The forces between the opposite charges are forming this electric field. Now, what is the barrier potential? A point is reached where the total negative charge in the depletion region repels any further diffusion of electrons, that is, negatively charged particles, into the p region, because we know that like charges repel each other. As a result, the diffusion stops. Now, the depletion region acts as a barrier. The electric field is a barrier to the free electrons in the n region, and energy must be expended to move an electron through the electric field. So, the amount of voltage required to move electrons through the electric field is the potential difference of the electric field across the depletion region. This potential difference is called the barrier potential. It is expressed in volts. The barrier potential of a p-n junction depends on several factors, including the type of semiconductive material, the amount of doping, and the temperature. The typical barrier potential is approximately 0.7 volts for silicon and 0.3 volts for germanium. Now we will understand the current equation. It is the equation of current where IDIF is I diffusion, which is the current caused by electron diffusion opposite from direction of electron. It means it is from P to N. In addition to diffusion current, there is another current which is drift current. We know that minority charge carriers also exist in both regions, that is, holes in N region and free electrons in P region. So, holes in N region diffuse through the edge of depletion region. Similarly, electrons in P region diffuse through depletion region. Both of these charge carriers experience electric field in the depletion region, which sweeps holes into the P region and electrons into the N region. These two phenomena create drift current. It is also called reverse current. It is from N to P. Now we will look at the energy diagram of PN junction and depletion region. Look at this figure. As you can see, the conduction band and the valence band in the N region are at lower energy levels as compared to the conduction band and the valence band in the P region. The free electrons in the N region that occupy the upper part of the conduction band in terms of their energy can easily diffuse across the junction. This is the junction. It means they do not have to gain additional energy and they temporarily become free electrons in the lower part of the conduction band in P region. After crossing the junction, these electrons quickly lose their energy and they fall into the holes in the P region valence band as shown. As this diffusion of free electrons continues, the depletion region begins to form. As a result, the energy level of the N region conduction band decreases. This decrease in the energy level is due to the loss of higher energy electrons that have diffused across the junction to the P region. Here I am showing an animation which is explaining the energy diagram of PN junction and depletion region that I have discussed in the previous slide. So have a look at this animation. When electrons diffuse across the junction, they fall into the hole and as a result, depletion region is formed. Now look at it again. The conduction band in N region is at lower energy level as compared to conduction band in P region. So when these electrons diffuse across the junction and enter P region, they lose their energy and fall into holes in valence band in P region. As a result, depletion region is formed. Now look at it again to make it more clear. When these free electrons diffuse across the junction and they enter the conduction band in p region, they lose their energy and fall into holes in the valence band in p region. As a result, depletion region is formed.